Okay, hello everyone. In this video we will just be going over nucleophilic substitution, just giving a general overview on nucleophilic substitution of alkyl halides. So let's first agree that alkyl halides, that you have a R group, any alkyl group, and it's connected to a halogen, whether it's a chlorine or it's a bromine or it's an iodine, any of the halogens that we actually have. So if you have an Rx, that's your substrate. If you have a nucleophile as an OH minus, when the nucleophile OH minus attacks that substrate, which is now going to be your electrophile, it would replace the X, which is the halogen, to give you ROH, which is an alcohol. When the OH minus attacks the Rx, or OR minus is the nucleophile. When it attacks the Rx minus, it will just replace X, and that will give you ROR. Now we have made an ether. When you have any carboxylate, R group could be anything, and then you have COO minus. Now as a nucleophile, it's not a fantastic nucleophile, but it's considered to be a nucleophile. It's a negatively charged species, attacking the Rx, kicking out the X group, and now we are forming an ester. If you have a CN minus, kicking out the X, you're going to form a nitrile. If you have another halogen, kicking out the previous halogen, giving you another alkyl halide. If you have any amine, such as a primary amine, for example, attacking this one and just kicking out the X, it will just give you a secondary amine. If you have an RS minus, which is a very, very strong nucleophile, kicking out the X, and that will just give you a sulfide, RSR. So it's very easy and very clear when your leaving group is X, is like a halogen. But sometimes that's not the case. So what would you do if your leaving group is not a good leaving group? Because normally our X, the leaving group X, is normally a good leaving group. When it's chlorine, when it's bromine, when it's iodine, when it's something like this big group, because when that one leaves, the negative charge on the oxygen can just be delocalized perfectly. When you have here a chlorine on a tertiary carbon, or when you have a carboxylate, again, all these leaving groups can just stabilize themselves and stabilize the negative charge upon leaving. So these are considered to be good leaving groups, but sometimes we can end up with a leaving group like an OH. We can have a leaving group like an OH or OR. What would you do in that case? These are very bad leaving group under normal cases and normal conditions. So far, that's what you have learned, that OH and OR, bad leaving groups. What you need to do, you have to force the leaving group to leave. You have to convert the leaving group to become good leaving group. So the bad leaving group, you will convert it into a good leaving group. How will you do that? You will protonate them. How? You need an acid as a catalyst. And then the lone pair on oxygen, they love to grab protons. So it will just grab the proton, it will become protonated. Before the arrow, it's just an OH, it's a bad leaving group. After the arrow, it's an OH2+. Now the oxygen has a positive charge on it, which will make it a good leaving group now, because the oxygen is only thinking about one thing. How can I get rid of this positive charge? I am an electronegative atom. I don't want it. Now it has become a good leaving group. OR, before the arrow, it's a bad leaving group. When it gets protonated, again the O lone pair will just grab a proton, becomes protonated. Now we have a good leaving group, and it can just, like, perform a normal nucleophilic substitution. So that will be an extra step that you have to perform in order to have the nucleophilic substitution reaction happening. All the other rules will apply, but before you do that, you have first to make sure that you have a good leaving group. If you don't, you have to convert your bad leaving group into a good leaving group. From this part, you will just do the normal reactions and conditions for nucleophilic substitutions. I hope that was helpful, and I'm gonna make more videos to help clear any confusion. Thanks for watching.